It should at least be more stable. Oh, this one. No, I think that'll just mess things up. All right, thank you. And it's recording, and I think it's oriented correctly. So Mario doesn't hassle me. Come on, how many times did I do it sideways? What, 10,
Once.
20?
It was just once, not gonna lie. Then the rest were perfectly fine.
Yeah, I guess you didn't see the other classes then. All right, so Q1, Q2, we'll just keep it like that for now. And then I have something, a distance r away. We'll make that our point P. And the question is, so those are all in a line, even if it's not drawn necessarily that way. The electric field at point P. Somebody just walk me through it.
Do we know the charges on either?
Not yet. I'm going to put that in later.
So first, I guess you would calculate individually the field force, just one of them, and then the other one.
All right. Electric field. The couple times you've done field force.
Yeah.
Okay.
I don't know why I keep doing that. I think it's the gravitational force thing.
Okay. Or there's, I guess, in sci-fi, force fields. But all right. So the electric field from each of them. All right. So I guess K Q1 over. What's the distance?
L plus R squared. Or, I mean, that's like half, right? So 1/2 L.
All right, so half of L. So R plus half of L squared. How do you want to indicate direction?
That way positive.
All right, so one-dimensional problem, we got positive. Plus?
KQ2 over R squared. Or R minus 1/2 L squared.
This is not a dipole, this is just two charges. All right, so let's see if we can get something common here. We've got this R plus 1/2 L right here. R is bigger than L. If R were smaller than L, well, let's just go ahead and establish that. I guess R technically could be, but R is bigger than L. We'll eventually make R much bigger than L. So R is the larger number, so I'm going to factor R out. So I have K Q1 over R times, I guess it'd be R squared over 1 plus L over 2R, quantity squared, plus K Q2 over R squared, 1 minus L over 2R squared. So relatively straightforward. So let's add some new restrictions here. Q2 is equal to negative Q1, which we'll just, since I'm directly relating them, we'll just drop some subscripts here. So this becomes KQ over R squared, 1 plus L over 2R squared, minus KQ over R squared, 1 minus L over 2R squared. I now have common factors more than just what I had before. And so I can factor KQ over R squared out, and I'm left with 1 over 1 plus L over 2R squared minus 1 over 1 minus L over 2R squared.
Not a Q or epsilon.
That's a Q. Now, if L were tiny, so we're talking nanometers, and R were huge, as in terms of meters. In other words, if I had my two charges that were opposite of each other sitting over there near the pencil sharpener, and I'm standing over here, I am far enough away that the distinction in the distance from me to each charge is negligible. So if I am far enough away, in other words, if R is much bigger than L, this term goes to practically zero, it becomes insignificant. This term becomes insignificant. What I'm left with in parentheses is 1 over 1 minus 1 over 1, which the math people tell me is equal to 0. In other words, if I'm far enough away, then the electric field where I am right now is close enough to 0. Good enough for physicists. And it should be that way. I would expect that. So if R goes to L, then my electric field is practically a 0 vector. This is my electric field at +2. But let's let's assume that we're not so far away that they become indistinguishable. An analogy would be, if I'm close enough, I can see a blade of grass, but if I stand far enough back, I can't tell one blade of grass from another right next to it. At some point, they just are close enough to each other that, it's as if they're on top of each other. So we got some common denominators here. And so let's just work the fraction piece of it. Now let's see if I can find blue. I don't think we've used blue today. This becomes 1 minus L over 2R squared minus 1 plus L over 2R squared. Parentheses in the wrong spot. Divided by, and blue is not the best choice there, 1 plus L over 2R squared, 1 minus L over 2R. So basically I got a common denominator. Multiply the left side by this denominator, multiply the right side by that denominator. Classic fraction stuff. And so now on top I am left with 1 minus L over R plus L over 4, L squared over 4R squared. Minus, might be slightly off screen here, but anyone watching this will be able to hopefully follow along. We're stuck with green. 1 plus L over R plus L over 4R squared. Over 1 plus L over 2R quantity squared, 1 minus L over 2R quantity squared. So my numerator, we've got a bunch of stuff that cancels out here. And on top I've got negative L over, negative L over R minus L over R, negative 2 L over R. And denominator, I still have that thing. Oh, we can do better than that. A plus B, A minus B. So that's just going to be 1 minus L squared over 4R squared. squared. So, when it comes down to it, my electric field at point B is equal to, I've got KQ over R squared times negative 2L over R times 1 minus L over L squared over 4R squared squared. That comes down to what form do I want my final answer in? So give me a moment. In the right place. I've got one for there. Oh, that's right. I remember where I saw it. Yes.
What's the denominator?
The denominator here,
Yes.
that's R, because we had negative 2L over R, so that's this right here. And then divided that by 1 minus L squared over 4R squared. And then that whole 1 minus thing squared that. Is that good enough? Okay. So I know that R is bigger than L. So at this point, if we threw in one other restriction, it really depends on how close we want to make it. But L over R is some fraction less than 1, and we squared it, so it's going to be even smaller than 1, and we divided by 4, so it's going to even be smaller than that. So we can sort of have a crude approximation here of KQ over R squared, over R cubed, times negative 2L. Now, this is a vector here. Recognize that at this point right here, I have two charges. I made this one negative Q and this one Q. The negative one is closer, so it is going to have the dominant electric field at this point. So ultimately, the electric field is pointing towards it, assuming that's positive, that's negative. It is close enough so that we're not completely watching it out, but we're far enough away that we can, that fraction right there, this L squared over 4R squared, is close enough to 0. And I also introduce something called the dipole moment. If I take a vector pointing from the negative charge to the positive charge, the symbol is traditionally a P. Please do not confuse it with momentum, which looks exactly the same symbol. This is the electric dipole moment. It is equal to Q times the distance between them, and I'm going to put a little vector symbol over the L. It is from the negative to the positive charge, however you want to notate that. And so this equation here now becomes, well, there's my negative QL. Negative because it's pointing in that direction, in the negative direction. And so this becomes K, 2K, electric dipole moment, over R cubed. We can write it slightly differently, because what the heck, why not? Don't forget, k is equal to 1 over 4 pi epsilon sub naught, so I can write this as 2p over 4 pi epsilon sub naught R cubed. I could cancel out the 2 there, but in the flash sheet, it's written as, I guess, 1 over 4 pi epsilon sub naught times 2p over R cubed. So the flash knowledge, that's the way it's written. We're going to do one other dipole, then we're going to talk about how realistic is it. All right, questions about the electric field here? All right, I guess we should. And instead of starting generically, we'll just start straight out with a positive charge here, positive Q, or 8, whichever one you're dealing with. Q, negative Q. Distance between them is L. My dipole moment, the electric dipole moment is pointing up, again from negative to positive. Some distance, let's see, do I want to make R that distance, or ultimately it's going to get washed out, but, oh, okay. So that distance there is R, and so naturally that distance there would be R also. This angle here is theta. And I want to figure out this is my point P, so the electric field at point P. And again, just like we've done several times before, we find the electric field from each of them, add them together. So, what is the direction of the electric field at point P because of the positive charge? So I've got a number of people pointing all in the same direction. All right, I think we're pretty much a groundswell there. And we will go for the traditional stunning visual effect. So it is in that direction right there. This is the electric field at point P because of the positive charge. What is the direction of the electric field because of the negative charge at point P? All right, again, looks like we got a groundswell here. What will be the direction of the net electric field? You'll leave you to hang, Austin. All right, somebody else joined you. I thought you were answered earlier. Okay, yeah. We got 2 people in agreement. All right, 3. We're hitting that groundswell again. Yes, indeed. Because of symmetry. Positive Q, negative Q, it's the same distance from both. The horizontal components are going to cancel out. And we can work through the math there, but the horizontal components are going to cancel out. So ultimately, it's going to be straight down. That's the total electric field. Now let's calculate it. Very similar to what we had done not too long ago. We find the magnitude of the electric field here, EP negative, magnitude, KQ over R squared. magnitude of EP positive. Someone want to take a wild, bold shot at it? I'll take that as no one wants to take a wild, bold shot at the magnitude of the electric field at point P because of the positive charge. Yes, it is. Since I only care about the vertical, as you kids today say, vertical components, all I need is that one right there. This angle right here is theta, because that angle there is theta, because again, symmetry. I'm going to get the same from over there, so my EP total is going to be 2 times, because whatever the vertical component for this is, it's the same as that. 2 times KQ over R squared times the sine of theta. We do need to indicate direction. So, think down negative, up positive?
Down positive.
Fine. Down's positive, all right. So I have 2 KQ over R squared. Sine of theta. What is sine of theta?
Opposite of the hypotenuse.
Okay. Suppose I said theta was small. What's a decent approximation for it? No. It'd be closer to 0 if theta is small. It's as if everything that was done in 251 has not been part of your everyday life. Every moment of your waking hours. And then presumably you creep into your sleep too. I definitely know we did it with a simple pendulum. Other than that, I presumably we dealt with it some other time.
Sine of theta equals tangent theta equals cosine theta.
Yep. If theta is much less than 1, notice there are no units here, so it's implied radians. Then sine of theta is close enough to the tangent of theta, which is close enough to theta. This is the relationship here that we really want to exploit. Actually, we don't need to, sorry. In my mind's eye, I was making R the horizontal distance, not the hypotenuse. It would end up to the same place anyway. Sorry, that was a diversion. Opposite of the hypotenuse. What is sine of theta then? What is the opposite over the hypotenuse?
Half over R.
So the 2 and the 1/2 cancel out. I'm left with KQL over R cubed. Again, make sure I didn't make some careless error. Because even though the cool kids do that. Okay. Now it is downwards, opposite the direction of our electric dipole moment, so we can of course express this in terms of our electric dipole moment. There's the magnitude of the electric dipole moment, and so this would be the negative K P vector, or electric dipole moment over R cubed, which is 1 over 4 pi epsilon sub naught P over R cubed. Yeah, wow, indeed. All right, here we go.
Question.
Yes.
What happened to the negative?
Oh, what happened to the negative? Because P is going up, but my vector was going down.
Oh,
Yep. So, oh, wait a second. Oh, there should be a negative there. I assume that's what you're pointing out?
mhm.
Yeah, sorry about that. Make sure it didn't, yeah. Other questions, comments, concerns? All right, realism of dipole. Actually rather realistic. Because if I expose an atom to, well, there are certain molecules that are already polarized, like a water molecule is already polarized. Because a water molecule got the main oxygen right here, and you got the two hydrogens, which are like 106 point something degrees off. It's been a long time since I've done chemistry. Somewhere in there, give or take. But the hydrogen atoms tend to be on one side, because they're sharing electrons right here. We basically have a positive side exposed and a negative side exposed, and so this is naturally polarized. It is because it's polarized, you can find a sort of an equivalent Q and negative Q and a certain distance apart. When you expose a dielectric to an electric field, it will polarize. It will pull electrons onto one side or the other. Similar to what we did in the demonstration with the Van de Graaff generator, and I took the packing peanut and it flew towards it and then bounced off. It flew towards it because it got polarized and then attracted. So, dipoles, something that if you get into electrical engineering, you will explore in much more detail. Who are the future electrical engineers in here?
He's not here. Zach.
You said Zach?
Oh, yeah.
Okay, so we slowly get rid of the electrical engineers. Okay. Future engineers? Oh, okay. Just curiosity.
Mechanical.
Mechanical.
Simple. Simple.
Computer. Computer. Mechanical.
Okay.
Technology.
And,
Nanoscience minor and computer science major.
okay, and Precious, I don't think you,
Biochemistry. I knew it.
there's a hesitation there, and I thought it's coming.
Yeah, I didn't want to tell you.
My daughter took this course, ended up, her degree falls under the English department. And so it got her out of the will. She was doing some communications major thing. I mean, she had gone through the, I guess, Calc 3 here and this course, and her friends were sitting around, had some calculus question, or calculus problem they're having issues with, and she knew enough calculus at this point, and she chimed in. They just were so unexpected from a communications major to have known that. Sorry, my mind just shot off on a tangent there. All right, so back to where we were. Jitu Kombuka. And what is G2 Kombuka?
Work.
Wow. So I have a dipole here, and just to keep track with my notes, there we go. Just sort of put the positive side on the positive there, negative there. some distance L between them. What is the direction of the electric dipole moment? All right, I got 2 fingers. Austin, was that an answer there, or?
I don't know.
Okay. All right, so I got 3 people now in agreement. And others are just staring. All right, so there are 3 people who actually expressed an answer. How do you know the direction of an electric dipole moment?
From negative to positive.
Yes, absolutely, from negative to positive. Oh, I guess I should put a Q in here, negative Q and positive Q, not just negative and positive charges. See if I can write that slightly more neatly. That's supposed to be negative. Negative Q, positive Q. And what is the formula for torque?
E cross Q. E cross Q.
E cross Q?
Or electric, not electric, dipole cross electric charge.
Thinking back to from a mechanics point of view, we're gonna derive the,
R cross F.
yeah, that's what I'm going for. Now R, what is R anyway in this formula?
It's the distance between the 2 particles from their centers.
From the momentum.
It is the length of the moment arm. Where's the,
Oh, never mind.
what is the moment arm?
In terms of this problem,
Yes,
is it the center of the 2 charges?
why?
Because they would rotate about the center.
Yeah, so it's from the axis of rotation, generally, axis of rotation to where the force is applied. So it's gonna rotate about that. I know that my positive charge is being forced in this direction. That's the force of the positive charge. The negative charge